Bayes' theorem is basically an extension of conditional probability. And Bayes' theorem actually takes into account new information. So if you have an initial probability and you are given new information that may affect that initial probability, then Bayes' theorem can actually calculate that new probability. So, and I'll give you an example in just a second, but here is the equation for Bayes' theorem. And what's important to note is that it does include, if the new event, it does include a new event and how that new event might impact your initial probability. So here's that example. A drilling company has estimated a 40% chance of striking oil for their new well. A detailed test has been scheduled for more information. Historically, 60% of successful wells have had detailed tests and 20% of unsuccessful wells have had detailed tests. Given that this well has been scheduled for a detailed test, what is the probability that the well will be successful? So here we have an initial probability of 40%. But now we have new information. We now know that we're going to be using a detailed test. And so how does that detailed test and this probability of a success impact our initial probability of success? So basically what our goal is to find the probability that we will have a successful well given that we have a detailed test. So if you plug in these, if you plug all of this into this equation, you'll get 0.667. And again, Bayes' theorem looks at the revision of initial probability due to new information. So given that this well was scheduled for a detailed test, the probability of success is now 0.667. Again, we had estimated that the success was going to be 0.4, but because we had that new information, we were able to update our probability. Counting rules are often useful in computing probabilities as well, and especially if you want to find the number of outcomes or your sample space. Counting rule 1 says that if any one of k different mutually exclusive and collectively exhaustive events can occur on each of n trials, the number of possible outcomes is equal to k to the nth power. So for example, if you roll a fair die 3 times, what could my outcomes be? Well, the first time I roll, I could get a 3, then the second I could get a 4, and then the third I could get a 3. Or I could roll it again another 3 times. It could be a 1, a 2, a 6. It could be a 5, a 6, and so on. And so what are the total number of possible outcomes that could occur? Well, we take k, which is the number of possible outcomes for a single roll. So there's 6 sides of the die, so it's 6. And then to the third power because we're rolling the die 3 times. And that'll give you 216 possible outcomes. So 216 possible ones of these sequences. And the probability of me getting a 1, a 2, and a 6 would be 1 out of 216. Here's another example. Flip a fair coin 4 times. How many possible outcomes are there? Well, again, an outcome could be, I could get heads, 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 or I could get a heads, 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 tails, or I could get a heads, heads, tails, tails, heads, tails, 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 all tails. And I want to know how many outcomes are there. What's the probability that I would get 4 heads in a row? Well, again, we can use k to the n power. So how many possible outcomes in one flip coin? There's 2. You either get a heads or a tails. And then I flip it 4 times. So 2 to the 4th is equal to. So what's the probability that I would get 4 heads in a row? Well, that's 1 out of 16. For counting rule 2, counting rule 2 says if there are k events for a first trial or k events on the second trial and k events on the nth trial, the number of possible outcomes, you just multiply them all together. So for example, if you want to go to the park, eat at a restaurant, and see a movie, and there are 3 parks, 4 restaurants, and 6 movie choices, how many different possible combinations are there? Well, all you have to do is multiply them together. So 3 times 4 times 6 is equal to 72 different possibilities. Here's another example. Doxy's clothing store offers 30 different pairs of shoes, 50 different shirt options, and 40 different pairs of pants. How many outfits can you make? Well, according to the counting 2 rule, again, you just have to multiply them together. So 30 times 50 times 40 is equal to 60,000. So there are 60,000 different outfits that I could wear from Doxy's clothing store. Counting rule 3 calculates the number of ways that a certain number of items can be arranged in order. So for example, if you have 5 books to put on a bookshelf, how many different ways can these books be placed on the shelf? And your answer is 5 factorial. So when you put the first book on the shelf, you have 5 different options. The next book on the shelf, you have 4 options. Then you have 3, 2, and then 1. So you have 120 different possibilities of arranging those books. Counting rules 4 and 5 deal with permutations and combinations. It can get a little tricky in calculating permutations versus combinations, so I would just like you to know the difference between the two. So permutations is the number of ways of arranging X number of objects selected from N objects in order. So for example, you have 5 books and are going to put 3 on a bookshelf. How many different ways can the books be ordered on the bookshelf? So instead of finding all the possible ways you could put those 5 books in order from the previous example, from counting rule 3, this time we're only picking 3 of those 5. And in this case, the order does matter, right? That counts as a different sequence. Combinations, on the other hand, is the number of ways of selecting X objects from N objects, irrespective of order. So you have 5 books and are going to select 3 to read. How many different combinations are there, ignoring the order in which they are selected? So again, the difference between combinations and permutations is that combinations, the order doesn't matter, whereas permutations, the order does matter. The way I like to think about it is if you have a locker combination, and really should be a locker permutation, because the order of those numbers that you put into the lock do matter. And that's the end of chapter 4. Now I know it may be a little bit unclear about what exactly I am expecting from you out of this chapter, so because of that I did want to go over this reading guide. I would like you to know the definition of all of these terms here. Know that an impossible event and a certain event, for an impossible event the probability is 0, whereas for a certain event, absolutely certain event, the probability is 1. The closer it is to 1, the more probable it'll happen, and the closer it is to 0, the less probable it'll occur. I'd like you to know the difference between these 3. You should be able to identify these simple event, joint event, and the sample space. And know that you can use a Venn diagram as well as decision trees to examine or visualize probabilities. We can also look at contingency tables. For these contingency tables, I would like you to be able to identify those simple probabilities and those joint probabilities. I would like you to know what mutually exclusive events are, if you can identify them, and what their characteristics are. Same with collectively exhaustive events. Can you identify it? What are characteristics of collectively exhaustive events? For the general addition rule and conditional probability, I don't need you to calculate those, but I would like you to know that we can calculate the probability of one event or another event, and we use a general addition rule for that. And then conditional probability is the probability of an event given that another event occurs, so that we can calculate these 2 probabilities as well. I'd like you to know what independents mean, and if you can identify independent variables. Marginal probabilities, I think this was misplaced, but make sure that you can calculate those marginal and simple probabilities from those contingency tables. Know what the Bayes theorem is. You don't need to know how to calculate or plug those numbers in, but do know that it is a type of conditional probability a way to evaluate conditional probability, and that it allows us to update initial probabilities if a new event or new information comes. For the counting rules, please know how to calculate counting rules 1 through 3. So basically you're finding the total number of possible outcomes in those. And then for counting rules 3 and 4, I just need you to know the difference between a permutation and a combination. So hopefully that sums up everything. I know probability can be very, very confusing, but again, as I mentioned at the beginning of the chapter, we do need to have a basic understanding of probability because so much of statistics relies on probability.